record. Yeah, if I have the time, I will share with you the recording on this WebEx platform. Although we'll see how it goes, because WebEx will be discontinued for UTM subscription. UTM will discontinue WebEx starting 1st of April. So we are at the 11th hour now. Maybe in a couple of days, we are not going to be able to use WebEx anymore for online classes. All right. So let's see if we are able to retrieve the recordings by then. Afterwards, we will not have any, access to WebEx and even their recordings. So I hope I am able to share with you the lecture online link for today's lecture. Okay, then. I actually have the slides again uploaded, but then I'm having a little technical difficulty to make it visible to you, right? Let me see. All right. Let me see. It's already here. Make available. Okay. Edit. I'm trying to change the settings here so that you are able to download the slides. First of all, I made a setting changes. Can someone or anyone download this, access and download this week 2A slides, pure substance? Oh, hang on a second. Show. Oh, okay. All right. I would bet it's already available now, yeah? Let me just hide the rest. It's not time yet. Please download the first slides, yeah? Oh, there's a lot to hide here. Hide, hide, and hide. Okay. So hopefully y'all don't download the slides, the next ones or the exercise. We are not there yet. Okay. This one, please download it. Week 2A. Well, it's supposed to be week 2A, but we were on holiday for the first session of the week. So let's say it's week 2B now, okay? So please download these slides. I will refer to these slides as we go along. All right. So now I'm sharing with you my screen. Are you able to see the screen? Please give a thumbs up. Okay. I noticed there are additional class members, right? Additional students in today's class compared to last time. I believe y'all didn't, your additional students didn't attend last time. Maybe you had issues registering the course. Maybe you added, very recently during the add delete course period and so on. It's okay. We will get to know each other as we go along, right? Okay. First of all, again, for those who haven't met me before, during last class, again, my name is Talha. You can call me Dr. Talha, right? I teach thermodynamics alongside Dr. Wira. I'm teaching section 1. If you are in the wrong section, please exit this session now. Section 2 is with Dr. Wira. So for today, I will actually continue a little bit on the basics of thermodynamics. All the definitions were not fully covered in last class. And then I will continue with the next lesson, which is on pure substance. All right. Let me see. I am sharing my screen, but Do you all see the slides or do you all see something else? Can I know if you all are seeing the slides, not other, views? Any response? Thumbs up or at least? Okay, Muiz is saying not seeing the slide. So let me reshare this image again. How about now? Okay, great. Thank you, Muiz, for the feedback. All right. Cool. So if we look at the CI, right? The CI tells you that there are 15 weeks. And along these 15 weeks, the first 2 weeks we'll do it online. And the next ones, of course, we will do it in class, right? Physical. We will try to cover phase changes for pure substance. And then, as we go throughout the semester, we will cover all these topics in the thermodynamics course. You will have 2 assignments. I'm expecting assignment 1 is by the mid-semester break, for which the test will be after, all right? I will not do test before an assignment. The assignment is there to prepare you for your test. And then assignment 2, we will cover the closed system and open system. So closed system for assignment 1 and open system for assignment 2, right? You'll get through open systems stuff or business later after the mid-semester break. Please forgive me, I have to entertain someone at the door. Okay, sorry about that. Let me reshare the screen. Okay, so this is roughly what we will go through for the semester, right? For test 1 and test 2, we don't know yet the exact date. I will discuss with the other course lecturer. We will finalize the dates. Of course, your tests will be combined with the other section because of the same timing of your sessions, right? So you have your Monday sessions and Thursday sessions going on in parallel for both sections, okay? All right. For today's class, right, we will recap a little bit on the concept of temperature and pressure, or, pressure and temperature, actually, the order, pressure first, then temperature. All you need to know about the technicals of pressure and the temperature when we talk about thermodynamics. And then we will go to some introduction of the phase diagram. We call this a PVT diagram. This is not a photovoltaic thermal. This is not electrical term. This is mechanical term. It's called pressure, volume, and temperature. Okay. So PVT is what we call it. Phase diagram is a better name. PVT sometimes you confuse with electrical engineering guys. They call it the photovoltaic thermal field. All right. So then we will move to properties tables. All right, and something new to you, I believe. This is something you will see only when you take thermodynamics course, unless you are repeating this course, right? So properties table, we'll do a little exercise, and then we will conclude this session today, and I'll ask for your feedback, okay? All right, so few objectives. I will come back to this objective at the end of our lecture today, because I want you to conclude what you understand from the lecture based on these objectives. As with a good engineering practice, you have objectives for your projects, for your task. Yeah, you will execute your whatever based on the objectives, and you will state whether you achieve your objectives or not. Okay, so at the end of this class, I will come back to these objectives and I will ask you, what did you learn? And I need your input on that. So please stay awake. I know it's 2 o'clock, 3 o'clock is sleepy time, but you have to commit for this next hour or two. Okay, so because I will ask you in the conclusion slides. All right. Distinguish absolute and gauge pressures. You will learn few things about pressure, although you have learned, back in high school or something. Okay, but pressure, and then you will be exposed to the zeroth law of thermodynamics, something that has to do with the temperature equilibrium. And then the third objective is for you to be familiarized, let's say remember all the key elements of the phase diagrams. Okay, there are three kinds of phase diagrams. You'll have the PT, which is the true phase diagram, and then the PV and the TV diagrams. And then you should be able, by the end of this lecture, explain the phases of the pure substance. The pure substance that we are considering today and through the rest of the course is water, right? Steam, water, H2O, whatever the name is, we are looking at water as the pure substance. Okay, so you are going to be able to explain the phases of pure substance, which is in this case water, through phase diagrams. Okay, and finally, this is what I expect you to achieve, is being able to read or extract data from the properties table. We will look at the properties table soon. There are multiple conditions of the table that you have to be familiar with and extract data from. Okay, now recapping, or let's say going through the basic definitions of pressure, right? Before that, is everything all right? Is anyone struggling to follow? Am I going too fast? I think I have to go fast for the introduction, but for the technical parts, I will slow down a little, okay? Okay, everyone okay? Good to go? Okay, all right. I guess that will do. So, when we talk about pressure in thermodynamics, there is a concept of pressure, right? There is also a concept of temperature. You probably have heard this before, but if you have taken maybe solid mechanics or, I don't know, basic physics, you know that pressure is actually simply a force acting on a surface area, right? And, the area, the smaller it is, the higher the force, right? Or the higher the pressure. Sorry, the force is constant, but if you have a smaller area, for example, you wear high heels, right? For the ladies, you step on your friend's toe, right? What happened if you step on your friend's toe with high heels versus you step on your friend's toe with normal shoes? Of course, the person will scream when you use high heels, right? Because the area is small. All right. So, force may be constant, but the pressure resulting from the force depends on the surface area that is involved. Okay, now this is a solid mechanics, right? Stress or pressure is force over unit area. Now, if we have a fluid, the same thing applies. If any of you have taken fluid mechanics course, it's basically the same thing, similar idea, except that, this time around is the area of the fluid, okay? All right, so the unit is normal. In SI units, we are dealing with SI units for the rest of the course. Although when you go to the workforce, right, most of the time you will deal with English units, right? PSI, pound force, pound mass, KSI, whatever, right? But for purposes of learning, right, to make the course more structured and easier to follow, we will limit to SI units. Newton per meter squared, which is force per area, okay? That is equivalent to Pascal. So the more elaborate units will be kilopascals, okay, 10 to the power of 3 pascals, okay. There's also bar. Bar means 10 to the power of 5 pascals, meaning 100,000 pascals. You can also have megapascals, which is 10 to the power of 6. Okay, so all these are, convertible to one and the other. Okay, you can convert from MPa to bar, from bar to MPa, bar to KPa, KPa to MPa, and so on and so forth. Okay. Bar is usually used in the practical applications. Okay, people in the industry like to report things in bar. Megapascal, kilopascal is more academic, meaning you see it in experimental, in charts, in tables. Okay, nonetheless, all these are easily convertible from one to the other. Okay. All right, so we have a few kinds of pressure. Number one is gauge pressure. Number two is absolute pressure. Sorry, vacuum pressure. Okay, we will talk about vacuum pressures later. Gauge pressure is when the pressure of the system that we're looking at is more than the atmospheric pressure. Okay, I will show you gauge pressure at work. Okay. And then we have the vacuum pressure, where the system's pressure is smaller or less than the atmospheric pressure. Okay, this is when a chamber or space is, the volume is taken out, okay, from the space, okay, using a vacuum equipment. All right. So if you look at this diagram, right, there's a relation between absolute, gauge, and vacuum pressure. So these are terms that you have to take note. Okay, absolute means total, right? Meaning you have for example, the gauge pressure. You have the gauge pressure plus the atmospheric pressure. For example, if I let me just skip this. If I were to pump tire, right, in the gas station, all right, you have to put it in, let's say 220 kilopascal, for example, or 200 kilopascals. Are you familiar with this? This is air pump at the gas station. I took this picture in, where is it? I can't recall. Oh yeah, this image source here. But you can find it in any gas station, right? This air pump, tire pump. This is 200 kilopascals, and the inside one is pound force per inch squared. This is the English unit. So usually a normal sedan car, if any of you drive a car, is between 200 to 250 kilopascals, right? So let's say it's 200 kilopascals. This amount of pressure is on top of the atmospheric pressure. Okay, so the reference point is 0, which is atmospheric pressure. Atmospheric pressure has a value. Okay, atmospheric pressure has a value of 101,325 kilopascal. But when you talk about gauge pressure, it is additional pressure on top of atmospheric pressure. Okay, so this 200 is 200 plus atmospheric pressure, which is 101 kilopascal. Okay, so then when we talk about absolute pressure, it is a combination of 101 and also 200. 101 kilopascal is right there at 0, and then 200 is your gauge pressure, which is the difference between the atmospheric and the measured one from your tire. Okay, so then the absolute pressure is 301 kilopascal, for example. Okay. Now that is regarding gauge pressure. Okay. So vacuum pressure, okay, it is a negative pressure, meaning the pressure that is much lower than the atmospheric pressure. That's why if you say this is atmospheric pressure, P vacuum, the vacuum pressure is below that. Okay, it is measured using a manometer. I'm not going to go through manometer calculations. This is something that is general knowledge based on your physics, high school physics, and so on, right? Okay. Atmospheric pressure. Let's talk about atmospheric pressure now. Something that we always disregard, or something that we always not take into consideration or not feel it, is the pressure by the atmosphere. We do not feel it, right? But actually, the atmosphere, which is surrounding the Earth, right, exerts pressure on the living beings on the surface of the Earth. Okay, it's just that the pressure is applied in all directions and it counterbalances, the pressure that we are supposed to feel normally, right? If this in one direction, then we will feel it. But because the pressure is in all direction, it counterbalances, the magnitude of the pressure that we feel. So that's why we don't feel anything. We can walk without feeling something on our head, right? But in reality, if you take a column of the air above us, right? Okay, it has a mass, right? Air particles have mass. Okay, I don't know what the mass is. You have to check your chemistry textbook, but air particles do have mass, So when you are down here, right? We are down here, and there are mass of air particles above our head, and then thousands of kilometers of height of this air column. There's actually a force, right? There's actually a mass that is exerted on our body, right? And this force or the pressure is measured using a barometer. A barometer, it measures atmospheric pressure. Okay. And the standard values are these values, right? 760 millimeters of mercury. Why mercury? Because the fluid that is used to indicate the pressure is mercury, right? This is mercury. Okay. The atmospheric pressure pushes down the mercury and gives a reading. 21.92 inches. These are just converted from 760 millimeters to inches. The numbers change because of the units. And in SI terms, it is 101.325. Okay, 101.325 kilopascals. Okay. Okay, so when you have an altitude, right? Altitude means ketinggian, the height of the location, where you have ground on the surface on the Earth. The pressure is higher. Why? Because there's a lot of air up here that is on our head. If we climb up a mountain, we are probably here, right? We are probably somewhere at the top. How many air molecules or air particles are there? Not sure, but definitely much, much less than if we were to sit down here, all right? So that's why the pressure is low in mountains, in high mountains, okay? The pressure is low. How about the temperature? What do you think? The temperature in the mountains, is it high or is it low? Is it cold or is it hot? How many of you would say it's hot? No? How many of you would say it's cold? Raise up your hands. What do you think? In the mountain, is it cold or is it hot? Okay. Yes, of course, it's cold. Why? Okay, good. Okay. Yeah, that's the correct answer. Okay, so it is hot. It is not hot. It is cold in the mountains because when the sun emits the sunlight, right? The radiation of the sunlight comes to the earth. Air at the atmosphere receives it first, the heat, the radiation of the sunlight. But unfortunately, there is nothing whatsoever in the outer space, in the atmosphere, to absorb the heat, right? Okay, Muiz, all right. There's nothing to absorb the heat. In fact, the air particles in the atmosphere is not a good heat conductor, right? It does not conduct heat well. So the heat from the sun just passes through the air, and when it reaches the surface of the earth, okay, the surface of the earth has a lot of elements that are good absorbers of heat, right? We have the a lot of things. We have if you have rocks, buildings, earth, soil, and whatever, right? You have human beings at earth on the surface of the earth. Uh, there are a lot of elements that are able to absorb heat, but up there in the mountains, not so much. Only air, even air, air could not absorb too much heat. Okay, so heat will just pass through air and it will hit the ground. That's why the ground will feel hotter. But how hot? Then people have to, or how cold? People have to conduct experiments and measure the temperature. Okay, I've talked about this. The gauge pressure is a mix of, sorry, the absolute pressure is a mix of gauge pressure and atmospheric pressure. Okay, absolute pressure is the pressure that we are going to see in tables. Okay, remember this. Absolute pressure, we are not going to read off from tables regarding gauge pressure. No, not the atmospheric pressure either. We are going to read properties of fluid from the table based on the absolute pressure. Okay, so this is the something that we just introduced to you. What is the pressure? There are many kinds of pressure, but from the thermodynamics table, from the steam table, what kind of pressure do we take? It is the absolute pressure. Okay, so please remember this at the back of your head. You can check these sources of YouTube if you want to learn more, but I'm going to skip over the YouTube videos. Then let's look at the vacuum pressure. It's also another kind of pressure, but wouldn't be of greater concern because at the moment we are looking at high pressure, high temperature regimes to run the energy sector in the world. A lot of things require high pressure and high temperature. But in certain cases, you want to make sure some system or enclosure is free from oxidizing elements. You will evacuate the particles, and you will use a vacuum pressure. Okay. I'm really sorry I have to take this call. Give me a second, yeah. All right, I'm back. Okay, so again, the vacuum pressure is a negative pressure. It's basically a pressure below atmospheric pressure. If you want to calculate the absolute pressure, you will just add up the vacuum pressure, which is in a negative sign or negative sense because it is lower than the atmospheric pressure. And then you will add up that with the atmospheric pressure. That's it. Okay. So if you want to go for an example here, you can just add up, the gauge pressure, which is 200, and also the atmospheric pressure to get the absolute pressure. Okay. And if you want to find the absolute pressure for a vacuum gauge is the opposite of a normal pressure gauge, right? This one is specific to negative pressures. It will suck an area where all the particles will be vacuumed, and the units are in negative. You see, negative 0.2, negative 0.4. These are in bars, but if you go with the black indicator here, it will be in inches of mercury, all right? So this is -30, -25, and so on. Okay, so you would simply add up this negative value and the atmospheric pressure to get the absolute value for the vacuum gauge. Okay, so nothing too trivial for those pressure concepts, right? Oh wow, this has some something with it. Okay, so these are basically the measurements that you can, or the equipment to take pressure measurements. These are all standard, yeah. Barometer. Nowadays we have a digital barometer also. Okay, now, oh my goodness, there are so many sounds that come with these slides. I hope you are not distracted by this. Can I just switch off the sound? Okay. For equilibrium, right? Simple concept. If you have a heated substance at 65, and then you have a heated substance at 90, and then you mix them together, finally they become 70 all over, right? And that is equilibrium. Okay, now I'm coming to the temperature scale. Most of the time, we will use Celsius, all right? Fahrenheit is English unit, but for this course, we will skip the English unit. Although if you go to the industry, you will more often than not, you will see this Fahrenheit being used. Now, Kelvin is the standard SI unit for temperature, not Celsius. If you take the difference of two temperatures, it doesn't matter. The unit doesn't matter. But if it's not the difference between two temperatures, then you have to refer to Kelvin. Okay, because the difference for Kelvin scale and Celsius scale are the same. All right. I'm not going to the conversion of the temperatures because we are not going to use Fahrenheit and Rankine. Rankine is just like a Kelvin for Fahrenheit. For Celsius to Kelvin, you must add 273.16. But if you ask me, sorry, 273.15. But if you ask me, I would accept also 273 conversion. Okay, without the 0.15. Okay, so up to you. At the end of the day, the answers will be quite negligible if you were to include this 0.15, but if you wish to include it, these two decimal places, it's also fine, no problem. Okay. You see here, minus 73, simple as that, 273. 0.15 if you want to be technically accurate. Now, this is the zeroth law of thermodynamics. This is where I'm getting at, right? The temperature data in the tables, they are measured using thermometers, right? And so the thing is with the thermometers is that if you measure two samples, right? You measure sample A and you measure sample B, okay? And for example, A is 20 degrees Celsius, for example. And the thermometer, right, reaches thermal equilibrium with sample A, and the thermometer tells you it is 20 degrees Celsius. Okay, the thermometer is a tool that indicates, gives us the number. The system A or the sample A does not give you any indicator, but it is 20 degrees Celsius. So both of these connect to each other. They will give you information. The temperature is 20 degrees Celsius, for example. Thermometer B, which is used to measure sample B, and at this instance, sample B is also 20 degrees Celsius. Okay. Now, we can say that A and B are in thermal equilibrium to each other. Although we never test them or mix them together, but because we use a third party, which is a thermometer, okay, 1 and 2, okay, you see, if two bodies are in thermal equilibrium with a third body, okay, the third body is the thermometer, okay, the two bodies in thermal equilibrium, which is body A and body B, with the thermometer, they are in thermal equilibrium with each other. So you would say, duh, what's the point? Of course, they are in thermal equilibrium with each other. They have the same temperature. But this allows us to use the same thermometer, right? And say or deduce that, okay, this thermometer is measurement is valid. Okay, without us mixing A and B, the thermometer will tell us that the value is 20 for both. Okay, so that is the zeroth law of thermodynamics, which justifies the use of thermometer in taking measurement, temperature measurement, okay, for data. Okay, now that is the end of the definition and the basic concepts, right? So wow, I spent half an hour, but okay. Now coming to the next topic, okay, pure substance. Now comes the question, right? This is just me, maybe 16, 17 years ago, when I was much younger. Grand Canyon in Arizona in the States. Now, it's not the picture about me that I want to highlight. My question is, what is the boiling point at this location, Grand Canyon, which is 2,700 meters above sea level? Okay. Ever wondered how fast you would boil eggs, or how long you would boil eggs at 2,000 meters above sea level? Okay. So pure water, right, undergoes phase changes. And you boil water, you cool off water, it will undergo phase changes. Okay. The only difference is how fast, how slow, depending on the pressure and the temperature of the surrounding. Okay. And the pressure and the temperature now also depends on the altitude, on the height of the location that we are testing the substance. Okay. So just now I asked you, what is the boiling point of water 2,700 meters above the ground? Okay, then it's not simply 100 degrees Celsius, 1 atmospheric pressure. You have to look into the thermodynamics properties of water at different pressure or different temperature of the substance. Okay, so now working substance normally is in liquid, vapor, or gas form. Okay, all substance in the universe can exist in either three forms. And the definition of pure substance is a substance that has a uniform properties and constant chemical composition. So when we talk about water, is purely H2O, not the water, tap water with chlorine in it, not the, Starbucks coffee. That's also water, but the water that we're talking about is not simply, any water. It's pure water, okay, 100% H2O. Okay, so please bear that in mind. And in the field of thermodynamics, substance typically we view it in the state of liquid, vapor state, and gas state. They have different names for it. For totally liquid, you have a different name. For totally vapor or gas, you have different name. We will go through these names, yeah? Okay. Any question before we move to the next lesson? Okay, those are just simple, let's say, simple concepts that you maybe are already familiar with. Now comes the heart of the things, which is the PVT diagram. Okay, so this is a PVT diagram. P stands for pressure, V for volume, and T for temperature. All right. In this diagram, there are regions where the pure substance are totally solid, which is in green there, when the right pressure, volume, and temperature exist. There's also when the substance is purely in liquid form, and it's purely in vapor form. Vapor means gases without any trace of liquid, all right? And then there is also a region where there is a solid plus vapor, okay, which is quite rare. But the more common one is liquid plus vapor. When you enter this region, that means there are both liquid and vapor for the same substance, okay? Okay, and then there is the three-phase line where all three phases exist, coexist, yeah? They exist simultaneously, solid, liquid, and vapor, all three. It's very unique. If you want, you can look up, it's very easy, you look up on YouTube, how does it look like to have solid phase, liquid phase, and vapor phase exist together at one time. Oh, very unique. You have to look. Okay, so but that one is very special properties. Depends, it varies across materials. And then you will have the critical point, which is usually the peak here. So critical point, we will view it in a better, a more clarified diagram using the PV and TV. But for now, critical point is just a turning point from a rising slope to a, decreasing slope, okay? So for water, the critical point for temperature is at 22.05 megapascals. And the critical point for temperature is at 373.95, where everything, you draw your phase diagram, it will not touch any liquid vapor dome regime. Okay, so this is the liquid vapor dome. Okay, I will tell you, or I will describe to you in greater detail when we go to PV and TV diagram. Okay, so this is a PVT surface, for example. So that one earlier was for expanding substance. Okay, this is for water, for example. And we also have for drinking substance. Okay. So basically, how do scientists or researchers or all these genius people come up with this? It's not rocket science. They just measure the pressure and the volume and the temperature for a pure substance, and they record the data. For example, the pressure here is a certain number, and the volume here is a certain number, and then they see whether the substance becomes a solid, or it becomes a liquid, becomes a vapor. That's all. Okay, and they do this countless of times, right? Numerous times, until they are able to come up with different sets of pressure, volume, pressure, temperature, volume, temperature, and so on. Okay, and then they map all together into this one single PVT diagram. Okay, one interesting thing is this ISO bar line, right? ISO, you recall from the last lecture, ISO means constant, right? So constant, bar means temperature, so constant temperature line. If it's an isothermal line, it's a constant temperature line. We will get to this once we draw the individual PV or TV diagrams, okay? But for now, this is the combined map of the PV and T in a single diagram, okay? Now, the more important one is the projection of the PVT diagram, just like you learn in AutoCAD, right? I think some of you, I taught AutoCAD. You learn the surface projection, right? If you project the 3D object to the side, to the top, top view, side view, and so on, you will see different results. Okay. If we project on the PT diagram, okay, you will have something called the phase diagram here. Okay, you see, this is pretty much standard for water. You have the solid phase on the left, you have the liquid phase on the right, and you have the vapor phase down here. Okay, this here is the critical point where all three phases coexist together. And then you can have your PV diagram if you project like here. Okay, PV. Okay, and then you can finally have your TV diagram when you project to the bottom. Okay, so our semester, our course here will deal with most of the time PV and TV diagrams. Okay, PT diagram, you can have some information on the phases, but the more critical one is the PV and the TV diagram. Okay, we will deal with a lot of these things, PV and TV diagram throughout the semester. Okay, phase diagram. This is a PT diagram. You can see that if we took the projection, okay, the left side is solid, the right side is liquid, and the bottom side is vapor. Okay, the critical point is up there. It's quite difficult to make some information of the critical point from here, as it is much easier to do the same in PV and TV diagrams. Okay, but you know here, beyond this temperature and beyond this pressure, things will be not dependent on the it will automatically be a vapor. Okay, beyond the critical point. And this point is, again, as I told you earlier, is a 3-phase point. Okay. Okay. When you have a line that connects a solid and the vapor region, it is called a solid vapor line. When you have a line that is a boundary between a solid and a liquid region, it is called a solid liquid line. And when you have a boundary or a line that connects or that separates a liquid and vapor, you will call that a liquid vapor line. So this is all, terminologies of vocabularies that are there in the phase diagram for PT diagram. Yeah. Okay. Now this is the more important one. Okay. The PV diagram. I want you to remember by heart, not just take this as new information. I want you to remember this by heart. PV diagram will always have the vapor dome. Okay, it's not an iron dome. Nowadays, the conflict with the war in the Middle East. The Western blocs have iron dome, iron sling, and whatnot. Yeah, and it's not that kind of iron dome. This is a different dome. We call it what is it? It's called the saturated liquid vapor mixture dome. But let's call it just the vapor dome, right? Or the mixture dome. This dome is unique. It's not simply there because I like to draw it. No, it's there because there are experiments that were conducted, yeah, by scientists of the 1970s, 60s. Even our fathers were not born yet, maybe in the 50s, in the 40s. Yeah. After the World War, people in the Western Bloc, they want to show, who is more superior in terms of knowledge against the Soviet bloc. That was Cold War time, and scientists were deployed to conduct as much experiments as possible. All those are history. But anyway, scientists in the 60s, 70s, they conducted experiments to show, the different phases of pure substance using these diagrams. Okay, so when you see this region, right, it's compressed liquid region towards the left of this dome. We will get into how this dome is created, but for now, to the left of the dome is a compressed liquid. To the right of the dome is superheated vapor. Okay, by hook or by crook, whatever the diagram is, left side is compressed liquid, right side is superheated vapor. These are all the vocabulary that you have to remember. Compressed liquid basically means liquid, 100% liquid. Superheated vapor means 100% water. 100% gas. Just gas. No water, no mixture, just gas, just vapor. Anything in the middle is the mixture of liquid and vapor. Okay? And here is the critical point. Okay, it's a unique characteristic of the PV or TV diagram. You have to remember the critical point. There are only two values. for water. Okay, the values that are two values I already mentioned earlier. Right there. 22.05 MPa and 373.95 degrees Celsius. Okay, coming back to the PV diagram. Okay, this point here is called the saturated liquid line. Okay, along this green line all the way to the critical point on the left side, before the critical point, is called the saturated liquid line. Meaning it is at this point, the last point where 100% liquid becomes less than 100% liquid. The last point. Towards the right, you go into this dome. Yeah, for example here, right? This is the last point where, you know, this is all liquid, right? All water, all liquid water. This is the last point before the 100% liquid water becomes a mixture of liquid water and vapor water, which is inside here, inside the dome. And then you come, you travel all the way, you know, this is maybe 100% liquid, 90% liquid, 10% vapor. Okay, you heat up, maybe you apply more and more, oh no, not more heat, it's pressure, so it's pressure based. Okay, so here you will have maybe 80% liquid and 20% vapor. Maybe here already down to 50% and 50%. Down here, right here is maybe already 20% liquid and 10% to 80% vapor. All the way until you reach this point, this is 0% liquid, 100% vapor. Okay, so this point on the saturated vapor line, green on the right side, is the 100% vapor line. The first instant where the mixture is gone and is 100% in vapor state, in gas state. And beyond that is already 100% gas lah. Superheated vapor is totally vapor. But the critical point is here, not the critical point regarding this top one. The switching point between vapor and liquid is determined from this line, saturated vapor line and saturated liquid line. Okay, any question? Any question? Okay, it is a little bit confusing, or let's say difficult to understand at first, but once you see it many times, you will get used to the terminologies and the physics behind it. Okay, this is at constant temperature. This from here down here to the right to the bottom, okay, is where the temperature is at a constant value. You only vary the pressure. Okay, this is the line where when you vary the pressure, the temperature is still the same. The temperature is still the same. You only change the pressure value. Okay, you only apply more pressure or less pressure. If you go to the left like this, you are applying more and more pressure, right? The pressure goes from 0 until a number here. If you go from the left to the right, you are reducing the pressure. Okay, you know how you increase or reduce the pressure? You, for example, you take a syringe. You know a syringe? A syringe is when you take your medicine when you were small, your parents will put in your medicine in the syringe, and they will push the piston, the piston head of the syringe, and you will have the medicine, the liquid medicine, coming out of the syringe and into your mouth, right? So yeah, when you apply pressure, you push the syringe, okay? That way you increase pressure, you apply more pressure. When you when you do that, you compress the air inside the syringe, right? When you release or pull the syringe, you will release less pressure. I mean, you are relieving the pressure, right? The air particles inside the syringe will feel less and less pressure, right? So that's how you vary pressure, okay? So now you can have different temperature, different isometric lines. Isothermal, not isometric, isothermal lines, right? Okay. If you plot higher temperature, right? But at constant temperature. For example, this T1 is 200 degrees Celsius. T2 is 250 degrees Celsius. Okay, it will come on top of this T1. Okay, like this. And if you have T3, which is 300 degrees Celsius, then you will have something here. Okay, if you have 320, you will have something up here. Okay, until you reach, what's the critical point? 300 and 300 something, right? You reach that critical point, you will not go through the dome. You will just touch that point and you go up like that. Okay. For other temperatures like this, you will go through the saturated vapor line, you go through the dome, and then you go up. Go through the right side of the dome, go through the dome until the left side of the dome, and then you go up. But at a critical point, you don't even go to the dome. You just come from the superheated vapor region, boom, hit the critical point, and then boom, go to the left side of the dome. Okay, so that's that. And then we identify this point as F subscript F, this point as G subscript G. Okay, subscript means the lower alphabet for the variable. Okay, F stands for fluid, G stands for gas. Okay, so this side of the vapor dome is the fluid, this side of the vapor dome is gas. Okay, so this point is G, this point is F. Okay, we will see how this F and G comes into play when we look at the tables, properties tables. Any questions? Anyone has any questions? Okay, no questions, I assume. Okay, there's one thing. Why this V, not this V? Some students who are very acute or very not acute, very sharp in their observation. Sometimes they ask why this V is big and this V is small. The reason is V. Let me see if I can draw. Oh, okay. So V is for volume, right? Let me see if I can plug in my pen here. Volume. This one, this small v is specific volume. What does it mean by specific? Yeah. Whenever you see specific, that means divided by mass. Volume is, what's the unit of volume? Someone tell me. What's the unit for volume? Anyone? This is a simple question. Come on, participate.
Meter cube.
Meter cube, okay. So, yes, Muiz is meter cube. So when we say specific volume, we will use a small letter. It will be meter cube divided by mass, which is in kilogram. So it will be meter cube per kilogram. Okay. Now, if I say enthalpy, The unit is in kilojoules. Maybe you haven't come across enthalpy concept yet, but if I say specific enthalpy, which is noted as small h, what do you think will be the unit? Kilojoule over kilogram. Okay. Another example, maybe if I have what else? Entropy. What is the unit for entropy? Meter per second squared, I think, or I couldn't recall. Okay. But if whatever the unit is, I mean, whatever the variable is, if it is specific, then it will be over mass. Okay. Why is it you have to use a specific volume or specific enthalpy and all this specific? Why? Because when we have a measurement that already takes care of the volume, we do not need to worry whether we are comparing between two different size of systems. Okay. We are not worried, oh, this data is for this temperature or this pressure is for a big volume, volume A. Oh, but the other temperature and pressure is for a small volume. No, we combine it into specific volume, specific variables, because we do not want to bother whether the data applies for a specific type of area or volume or enclosure or chamber or whatever. All we want to know is the value applies across all system, all setup, right? So that's why we go with these specific values. So it is one and for all, not dedicated to a single system or a single setup like this. Okay. Okay, now let's move on to the TV diagram now. Same thing, draw the axis, okay, and then draw the vapor dome. By the way, you have to draw this, you have to be able to draw this. So you must draw this. You must know how to draw this, okay? First of all, in your test, in your exam, your assignment, in your finals, this is a must. You must be able to draw, okay? If you're not able to draw this, then you're going to have troubles, okay? And then when you draw, you must know its critical point at the top. Left side is compressed liquid. And then the middle side is the inside of the dome is a saturated liquid vapor mixture. And then superheated vapor on the right. Saturated liquid line, saturated vapor line. This is all the elements that you have to know by heart. Okay. Now, the difference now, just now, the PV diagram, right? You had your things going this way, right? Right? But for TV diagram, you wouldn't have that, what you call, that direction of the line, okay? The line will be the other way around, okay? Going from the bottom on the left side, okay? Going from the bottom, and then it goes on a plateau, which is a flat line inside the dome, and then it will go up. Now, this line is called an isobar, right? It's an isobar, okay? Isobar means constant pressure. Okay, so same like the isotherm, right? Last time in the PV diagram, you have a constant temperature, but this time around you have a constant pressure line. Now this one, the one on top of it, is also a constant pressure line, but the value is higher. For example, here is 100 kilopascal, for example. Now this one will be 200 kilopascal, for example. Okay. But it must not go beyond the critical point. The critical point is some megapascals, right? So kilopascal, okay, you're fine here. Then if you go somewhere here, okay, maybe this is already 2 megapascal. I don't know, whatever, right? As long as it's below the critical point. Okay? And then you will have your F fluid side and gas side here. Okay. Any question? Okay, I'll let you a few seconds to process this. PV and TV diagram, they are similar except that the direction of the constant pressure or the constant temperature is the other way around. Okay. Okay, PV like this, TV like this. Okay, now that is how the diagram looks like. Now, how do you explain this diagram? Okay, before I go to this slide, I'm going to explain to you the physics behind it. So this is all liquid, all liquid. Okay, this region. Okay, this is TV diagram. So you heat up, right? You heat up. Okay, you heat up, and you know the temperature goes from here to here to here to here to here. At one point, the for example, if this is constant pressure at atmospheric pressure, 1 atm, or which is 101,325 kilopascal. For example, you know what happens? What's the boiling point at 1 atm? Does anyone know? It is 100, right? 100 degrees Celsius. Okay, that is pretty much standard, right? At the normal pressure, atmospheric pressure, it must be 100 degrees Celsius. So when you heat up, you keep heating up until 100 degrees Celsius. Okay. This is the point where the water starts to boil, right? The water starts to convert into gas, right? When you boil, when you see boiling process, water will be converted to water vapor, right? So here there is still water. Okay, maybe this is 90% water. You keep it 100 degrees, it's still 90%. Okay, there's some of it has become gas. Okay, this is 90% water, liquid, and then this is maybe 80. By the time you reach here, it's 50% liquid, and the other 50% is gas. Okay, by the time you reach here, it's still boiling, 100 degrees. This is 10% liquid and 90% gas. At this point, right? At this point, everything has turned into gas, right? At all this water liquid has turned into 100% gas. During this period, okay, the volume has expanded. Okay, why expanded? Why expanded? This is the volume, right? The volume from this much of water, this much until this much, it increases. The volume increases, right? The volume increases. Why? You have more gases taking up space. That's why. Okay. The more and more gas you have here, the more volume you get, okay, from the water. And when you increase the temperature all the way to, I don't know, whatever, Ts to maybe 200 degrees Celsius, everything will be in superheated vapor, meaning everything will be in gaseous form. Nothing will remain in the liquid form. Okay? So that is what is meant by the physical process of this phase diagram. Now, if you were to visualize it using a piston and what do you say? Piston assembly system, right? Okay. For example, you have this phase diagram. Okay, TV. For example, this is 1 atm. Okay, like I said earlier, 1 atmospheric pressure. Compressed liquid, 20 degrees Celsius is down here. Okay, down here. And then at state 2, okay, the second state, you still maintain the pressure, but you increase the temperature. Okay, it is at this point, which is the saturated liquid point. Okay, if you imagine the dome is here. Oops, like that. Okay, but let me erase that. That's just for visual purpose. Then state 3, you have 1 atmospheric pressure, still at 100 degrees Celsius, 100 degrees Celsius. But, you know, some of the water has become vapor. And then you come to state 4, okay, it has now become known as saturated vapor. Okay, saturated vapor. And that's the term that you have to remember lah. Okay, it's called saturated vapor. 100% vapor, the first starting point of 100% vapor. And then you have state 5, which is still the same pressure, okay, but you just increase the temperature to 250 degrees Celsius. Now it has become superheated vapor, which is outside the dome. Okay, remember I draw the dome earlier. The dome is somewhere here. It's outside the dome already. Okay, so if you go with, oops, there's the dome there. Let me just erase that. I thought the dome was not there. Okay. So if you go with, different pressure, right? And this one is low pressure, even higher, and then it's 1 atm, and then 1.5 atm, 1.8, whatever, right? Until you reach the critical point where the temperature here is 374.15, okay, degrees Celsius. That's all you need to know, okay? So try to play around with this idea, right? Try to match the state, with the phases that the state comes with, right? And then you'll understand the phase diagram. Okay. So why this dome happens? As I told you earlier, it's not because I like to draw it that way. It's because when the scientists, they collect data for different pressures, right? Pressure values, okay? For example, if you take more and more, right? If you take more like this, right? More like this, you will see that these points, this what you call this, these saturated vapor points and saturated liquid points, they connect with one another. Okay, they naturally connect until they form this dome. Okay, if you draw multiple lines, right? If this is 0.1 atm, 0.2, 0.3, 0.35, and so on, it will connect this line. It will connect this line into a dome. Okay, so that's why the invisible dome there, otherwise I would not have made this up. And this is the dome that happens because of the multiple data, okay, thermodynamic data. Okay, any questions? Okay, shall we take a break? Maybe 5 minutes. I want to take attendance. Let me just unshare my screen for a while. Attendance. Download. Yes. Okay, guys, let me just continue sharing the screen. I am not sure if everyone attending today's session or class has their names on this list. But in case there is not, please let me know. Maybe you are in the middle of registering courses and so on. So what I'm going to do is I'm going to tick everyone as present. I will call out your names. If I don't hear any response, I will assume you as absent. And then if you think your name was not called out, please let me know so I can add your names further. Okay. Aditya, is that the correct way to say it?
Yes, Doctor.
Okay. Aditya, okay. Christine.
Yes, Doctor.
Okay. Go, I saw you earlier. Huang. Do we have Huang Changming? No. We have Kiang.
Yes, Doctor.
Okay. Lee Zhenghao. Lee. Do we have Lee Zhenghao? Okay. Lim Yu Chuan.
Yes, Doctor.
Okay. Muhammad Israel.
I'm here. I'm Huang Changming.
Huang Changming. Okay.
Yeah, I'm here.
Okay. Muhammad Israel.
Here, Doctor.
Okay. Nivita.
Here, Doctor.
Okay. A few familiar names for me. Nur Alia Suraya.
Here, Doctor.
Okay. Nur Hasha Zahira.
Here, Doctor.
Okay. Nur Ain Atika.
Ada, Doctor.
Okay. Teo Yu Ting.
Yes, Doctor.
Okay. Yo Yi Ying.
Yes, Doctor.
Okay, great. Okay, please tell me if your name is not here. Anyone? Mois. Okay, Mois. Anyone else? Okay, just Mois. Muhammad Furat to me. Furat, are you a local? I bet you are not. Where are you from, Furat? Can I hear your voice?
Assalamu
Yes. Alaikum salam. How are you? Where are you from, Furat?
alaikum. I'm from Tunisia.
Tunisia. Okay.
Yeah.
This is your second year or first year?
First year.
First year. So then welcome to Malaysia.
Thank you.
All right. Thank you, Furat. Anyone else? Okay, so then I have 15, 16. Okay, if there is no one else, then I will stop here for the attendance. Okay. Let's see. Okay, so far, is there anything that you'd like to ask before I go into the next few slides? The next few slides is on the next objective, which is to familiarize yourself with the properties table. Yeah. Okay. Now, I don't want to go yet to the dryness fraction or the quality. Okay. I want to show you the properties table. Now, if you go to your e-learning, right? If you go to your e-learning, where is the e-learning? Okay. I already uploaded the steam table. Okay, this is the property tables for a lot of things, but one of the tables or a few of the tables are regarding steam or water, saturated water table. Okay, sometimes it's called the steam table, sometimes it's called the properties table, whatever it is, a table. Okay, so what you want to do is open this table. I hope you are able to retrieve this. Let me know if you are not able to get to this table. It's in your e-learning under the general tab. Inside it, you have announcements, course information, textbook, property tables, and this is the property table that we are looking at. There are a few versions of the property tables, depends on the group of scientists that developed it. But basically, what we are using here is the 1996 table, which is perhaps the one of the recent ones. 1996, some of you were not even born yet. But it's the most recent one because it's comprehensive enough. And to reproduce a comprehensive table would require a lot of capital resources, fundings, and that's why the property table, once it's there, it's 1990s stuff. It's going to be reused all the time. So it's 1996 version. I have the 1972 version. I'm not going to use that, but it has similar values. Please use the one that I uploaded. That one is quite the recent one. And the textbook is also there. If you wish to refer textbook, e-textbook, please go through examples at your own time. I'm not going to go through the textbook reading at your own time. Okay, so the properties table is there. Okay, please click on it, and our tables of interest will be tables A4. Okay, tables A4, A5, and A6. Okay. Now, table A4 is called the temperature table for water. Okay, temperature table, meaning you have, let me just blow this up a little bit. Okay, you have a variation of temperature, okay, on the left side. Okay, it starts from 0.01 degrees Celsius. And for this temperature, right, you will see that it corresponds to different temperature, okay? Different pressure in kilopascal, okay? And for this temperature, you will have a lot of properties. The saturated liquid specific volume, the specific volume at saturated vapor. Where is this F and G, VF and VG? Basically, it's on the left and right side of the vapor dome, okay? Remember that we drew the phase diagram, the PV diagram, the TV diagram. F and G are 2 points on the dome. F is on the left, G is on the right. Okay, so when you say saturated liquid, VF, that means where? That means it is right there. Okay, F, you see F there? That is the value of V, specific volume, in the table. Okay, you see that? VF is, for example, the temperature is now, for example, in this figure, F lies at 200 degrees Celsius. For example, you look at 200 degrees Celsius, it's way down here, it's way down there. 200, okay, 200 degrees Celsius. The VF is 0.001157. Okay, you see there? VF is in the third column, and you see 0.00157. How about VG value? Is in the fourth column. It's the specific volume at the saturated vapor line. The value is 0.12721. Okay, you don't need to calculate, you don't need to do or run experiments. These are experiments ran for hundreds of times, okay, and the data is here. Okay, some scientists, they already tabulated this. You only need to extract the data from here. Okay, you don't need to do anything. Okay. If there is a enthalpy value that you have to look at, that particular temperature is also there. If there's an internal energy value, it's also there. There's an entropy value, it's also there. The only thing that differs is one is V for volume, one is U for internal energy, one is H for enthalpy, one is S for entropy. Okay? So for all variables, for all thermodynamic properties, you have the sub F and also you have the sub G. Okay, one for fluid, one for gas, one for totally liquid, and one for totally vapor. Okay. Now then, students ask me, Doctor, what is UFG? What is HFG? SFG? What is this FG subscript stand for? That means the difference between G and F. Basically, you subtract UG, UF from UG, or for example, UG minus UF, HG minus HF, SG minus SF, you will get the middle one, which is SFG, HFG, UFG, and so on. The only one that is not provided is the VFG, which you can calculate easily by subtracting VG minus VF. Okay? So if you wish to find VFG, sometimes you will wish to find it because you will use the concept of quality. Well, you can subtract these two values. Okay? If you don't know what subtract what, you know, is it F minus subtract or minus G or G minus F, then just look at the larger value and then minus the smaller value. Usually it's like that. Okay? All right. Any questions? Okay. So now, if I ask you, right, slides, for example, slides 25 until 27 is basically the tables which I show you. But if I ask you, right, okay, example 2.1, determine the water boiling temperature at 100 kilopascal and 5 megapascal. So two cases here. One is the boiling at 100 kilopascal. Case number 2 is boiling at 5 megapascal. Now, which table are you going to use? Now, for A4, table A4 is for temperature, okay? Saturated water temperature table. You go to table A5, table A5 will tell you the properties at varying pressure. Remember earlier, the leftmost column is varying temperature. Now the leftmost column is varying pressure. Okay? You see 1 kilopascal, 1.52, 2.5, blah, 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 right? And the corresponding temperature is on the second column. This is the temperature that we not vary. We do not vary this temperature. This is the corresponding that corresponds to this pressure. Okay? All the properties are here. Okay. Specific volume, blah, blah, blah. Now, what did the question ask? 2.1, example 2.1. Determine the boiling temperature at 100 kilopascal. Okay, at 100 kilopascal. Look at the table. 100 kilopascal is down here. 100, right? 100. The corresponding boiling temperature, the saturation temperature here is 99.61. See, 99.61. Oh, hang on. Yep, 99.61. Okay. So it's slightly lower than 100 degrees Celsius. Why? The reason to that is the pressure is slightly lower than the atmospheric pressure. Okay. Atmospheric pressure is 101.325 kilopascal. If you go with 100.1.325 kilopascal, then you will get 100 degrees. Exactly. Okay. So let's say now, second example, 5 megapascal. I want to look at the table A5, which tells me the variation in pressure. Okay, pressure table. So 5 megapascal is 5,000 kilopascal, right? So this is in kilopascal. Okay, this left column is in kilopascal. So like it or not, I have to convert in my head. So it's how many kilopascals is there in the 5 megapascal? It's 5,000, right? 5,000 kilopascal makes up a 5 megapascal. So 5,000 is down here. Okay. And the temperature here in the second column is 263.94. Okay, degrees Celsius. Okay, like that. So that is the temperature. So what if we are given the temperature, right? 50 degrees Celsius, but we are asked to find the specific volume of water. Okay, at saturated vapor condition. Okay, it's saturated vapor. What is saturated vapor? Is it F or G? Vapor is G, right? Gas. So it's saturated, it's vapor, so it's G, okay, Vg. If it's saturated liquid, okay, then it's Vf, okay. If it's liquid water, if it's compressed liquid, it is another story. I will tell you about that soon. It is also Vf, okay, but the term is compressed liquid, which is the leftmost side of the dome. Okay, now you see 50 degrees Celsius at saturated vapor. Saturated vapor means all vapor. Okay, all vapor means the right side of the dome. Not the right side, the green line on the right side of the dome. So that green line is the G, represents the G, the gas. Okay, so we have to look at this time around. We are given the temperature. We are not going to look at A5. We are given the hint is temperature. So we have to look at A4. So A4, okay, temperature is 50. Okay, temperature table, temperature is 50. Okay, so what is Vg at 50? Vg, 12.026. Okay, 12.026 is the answer. Okay, saturated vapor is on the fourth column. And if you look at 50 degrees Celsius row, you will get 12.026. Okay, so 12.026, 12.03, very close. Okay, any question? Is there any question? No? Okay, it's pretty simple, right? Okay, let's look at the next example. Vg at 500 kilopascal. Okay, determine the specific volume of water, okay, V, at saturated vapor condition. So saturated vapor means G, okay. If saturated liquid means F, so it's Vg at 500 kilopascal. So someone tell me, what table are we going to use, A4 or A5? Tell me in the chat. Is it A4 or A5? Do I have access to the chat? Oh, yes, I do. A5. Okay, Kiang, you are right. Good. So A5 is the pressure-based table. Go to A5. You are given the information on pressure. So you will use the table that suits that information. Given 500 kilopascal. 500 is down here, 500. Vg for 500 is in the fourth column. 1, 2, 3, 4. Okay. So 0.37483. Okay, 4.3748. Okay, that's correct. Okay, so now, what if the system is inside the vapor dome? What if what we are looking for is inside the vapor dome? Just now, we were here, F or G, right? F or G, okay? There or there, F or G. on the two ends of the vapor dome. What if we fall inside the dome? Then we have this concept called quality. Okay, quality. Quality is defined or is called X. Okay. Basically, it's the ratio between the vapor and the mixture. Okay. The vapor, how much gas is inside, whether it's the mass of the gas, whether it's the volume of the gas, whether it's the internal energy of the gas, whatever, right? Whatever properties, whatever intensive properties, right? I hope you still remember intensive and extensive properties from the last class. So this is the ratio between vapor and the mixture of vapor and fluid or liquid. Okay, so basically, if you were to rearrange this formula, right? Substitute m, the mass, with the other properties, right? You will have the mass, or sorry, what do you call it? Volume, specific volume equals the volume of fluid plus the percentage, which is the quality, times the difference in the gases and the fluid volume. Okay, that is in terms of words, right? Let me just let me try to put this in mathematical form. Let's say okay, this is your TV diagram or PV diagram, right? Okay, let's say PV. Now, what you are looking at, the state that you're looking at is here. Just now it's F or G. Okay, no problem. We can just read it off the table. No problem. But what if it's here? What if it's here? Right? We have to use the concept of quality, X. If you rearrange this, it will become X times mg plus mf equals mg. Right? So basically what it's doing is linearizing the formula, right? So basically this X also can apply. This one is V equals Vf plus X Vg minus Vf, right? Okay, so this is Vf from the table, Vg from the table, Vf from the table. Okay, once you are given the quality ranges from 0 to 1. If it's 0, then V is Vf, you know, it's here. This is X equals 0. Okay, if X equals 0, then V equals to Vf, right? So your quality doesn't play any role here. That means X equals 0 means the quality tells you there is no vapor, So no vapor means here is the point of no vapor. No gases flying around. If X equals to 1, then V minus Vf equals Vg minus Vf. Then V minus Vf comes to the right side and cancels out with the other Vf. V equals to Vg. So when X equals to 1, this is when there is no liquid. So here is X equals to 1. There is no liquid. Okay? All vapor. Okay? No liquid or all vapor. All vapor. Okay, all vapor. 100%. Okay, so X is a measure of how much percentage vapor there is in the mixture. 0, no vapor. 1 is 100% vapor or no liquid. Okay, so you will use this formula VF plus X times VG minus VF to find the actual V, the actual specific volume. Okay. Okay. If I just exit this slide. Okay. Now we can go with the example. We can go with this example 2.3. Okay. A system contains some liquid vapor mixture. You see, liquid vapor mixture water. Okay, 100 degrees Celsius and X equals 0.8. You see that? Okay, there's a quality now, meaning the state of the liquid or the water is it's a mixture inside the vapor dome. What you have to do is apply the formula. Okay, look at this formula. So the volume fraction there for that temperature and quality is what is it? X times VG minus VF. Okay, so you plug in, you find the VG at 100, you find the VF at 100, and then you multiply by 0.8. Okay, so basically you execute this, and then you get the answer. Okay, just plug in. I think there's a VF. There should be a VF, right? VF minus, right? I think you will get a slightly different answer. The correct formula should be V minus VF equals X VG minus VF. That is the correct one. Okay? So basically, there's a concept of quality if you are inside the dome. There's a concept of saturated liquid, VF, saturated vapor, VG, right? And then you can read them off from the tables. Okay. Now, you can extend those exercise to your own time. Okay. You can use this slide as a working example. I will go through table A6 in the next class. I don't think I have time for today's class to go through A6, but basically A6 is for superheated vapor, okay, meaning for the right side of the rightmost side of the phase diagram here. Okay, I haven't discussed yet about this side of the table of the diagram and this side of the diagram. Okay, you have this one already, this one and this one not yet discussed. We will discuss this. We will discuss this in the next class. Okay, we already discussed this one along this line, and then this one along this line. This one is G, this one is F, and this one in the middle is the X. Okay, the concept of quality X. Okay, so we've spoken about F, X, and G, but we have not spoken about the superheated vapor, okay, which requires A6, and then the compressed liquid, which is A4. Okay, we will discuss this later in the next class. All right, I think that's all that I'd like to share with you today. Now, coming to the conclusion, right? Now I want active participation. Just tell me if you do not like to voluntarily participate, then I will just call names, right? But before I call names, it's better to have a participation. Kindly let me know. What do you remember? What do you understand? about these objectives. You see, I laid down objectives in the early period of the class, and then I told you, okay, these are my goals for the class today. What you should know, what you should understand. Then I'm coming back to these objectives. What do you understand? Anyone? Okay, anyone can tell me what they understand or what they remember about the lecture for absolute pressure, gauge pressure, negative pressure, vacuum pressure, whatever. Can someone tell me? Anyone like to volunteer?
Is it pressure measured
Yes,
from
Aiden.
vacuum?
Yes, pressure.
Pressure measured from vacuum. Absolute pressure.
Absolute
Gauge
pressure.
is, yeah. Gauge
Yeah,
is
okay.
related to atmospheric pressure.
Okay, good attempt. Okay, thank you, Aditya. Aditya, are you a local student?
I'm local, so yes.
Oh, okay. Sorry about that. Okay. Yes, you are partially correct there. Absolute pressure is the total of the gauge pressure and the atmospheric pressure. Eh?
Yes.
Okay. And you know, in the tables, the pressure that you see in the tables. Okay, can someone tell me which pressure? Is it the absolute pressure, the gauge pressure, atmospheric pressure, vacuum pressure? Which one? Can someone help me out here? Which one? Absolute, gauge, atmospheric, vacuum? Can someone tell me? How about if I just randomly pick? Okay. Christine. What you think, Christine? You know, this is the part of the class that students are very uncomfortable. Every students who enter my class will for sure experience this name calling to answer question. Okay.
Doctor, may you
Yeah.
repeat the question?
What is the pressure that you see in the table? Yeah, this table, remember that we saw the table. You saw the table here, right? Okay, pressure, this pressure. What do you think is the pressure? If you remember, I told quite a few times in the lecture. Is this select from absolute, gauge, atmospheric, or vacuum pressure? Which one you think? It's okay if you get it wrong.
So vacuum?
Vacuum, okay. Good attempt. Vacuum pressure is again for the you know, vacuum cleaner, right? You suck air out from area, right? So you suck the rubbish into the vacuum cleaner. So unfortunately, that is very specific. The vacuum pressure is pressure for sucking and emptying an area. So actually, the correct answer is absolute pressure, the total of everything. So atmospheric pressure and the gauge pressure combined is the absolute pressure that we use in the table. Okay. Okay. Thank you for trying. Okay. All right. Zeroth law of thermodynamics justifies the use of thermometer. Okay. Now, I'd like a few volunteers to tell me what they remember of the elements of the phase diagrams. Okay. I give you one critical point. Okay. Anyone else would like to try before I call out your names? Yes, state what is there in the drawing of the PT and PV and TV diagram.
compressed liquid and superheated vapor.
Okay, who's that? Go. Okay, compressed liquid, correct. Compressed liquid, superheated vapor, correct. Okay, compressed liquid is on the left side of the dome. Superheated vapor is on the right side of the dome. Okay, anyone? What else can you remember from the phase diagrams? How about Huang? Are you there, Huang?
Yeah.
Okay. Can you try? What else do you think is there in the PV diagram, TV diagram?
Maybe I need some time to think about it.
Okay. How about I show you the slides here on the left side? Can you make something out of it? What else is missing there that we don't have in this table? Oops. Okay, what else can you see? Okay, slide 21, naming the conclusions. I put critical point, compressed liquid and superheated vapor. Okay, what else is there that is not in the table yet? Look at slide 21 here in your screen. What else? It's easy one. Okay, I have 1, 2, 3 items in the conclusion table, but there are still a lot more in the PV diagram there in slide 21.
I understand that quite well.
What is that? Maybe the line is not clear. Okay, let me give a hint. It is inside the dome. What is that? What does it say?
The standard vapor mixture.
Vapor mixture. Okay, correct. That is called the saturated liquid vapor mixture. Okay, good. Saturated liquid vapor mixture. Okay, there's a mixture inside there. Okay, what else? Okay, how about Kyang? What else is there?
Saturated liquid line.
Yes, and that one is on the left side or the right side?
Left side.
Okay, on the right side. How about right side?
Saturated vapor line.
Okay, thank you. Saturated liquid is F. Saturated vapor. Okay. All right. Explain the phases. Okay, I think this is this is quite extensive. It's already 3:55. Okay. Basically, the one that I told you from liquid to gas, you know, all those changes from liquid to 100% liquid to 90% liquid to 100% gas. All those are the phase changes of the pure substance that can be explained line by line in the phase diagram. Okay. Finally, extract data from the properties table. This one I cannot conclude yet because I haven't tested you yet. I just managed to give you examples, but I haven't managed to ask you and get correct answer from you. So what I like to do, now before we end the class is for you to join me on Padlet. I want to know what you are struggling with, what you find difficult for today's class, or what you wish I could explain better. Just log in using your Google account, and then you can just fill in your comments. Your comments will appear here. If you write more and more comments, it will shrink, or it will. Oh, it's not shrinking. Just write a simple comment. Whatever you think is, whatever you think is relevant to today's class. That you think you want more, you need to understand more or something. Okay, do you on time? I will review this next class, okay? And then we'll see what you are lacking, what you think I should have explained more, and then we'll go from there, okay, in the next class. Just if you don't have any Padlet account, just simply create an account and just respond to this questionnaire, okay? All right, any questions? Some of you already here. It's okay. Don't feel shy. Just fill it. Just take active participation in class, and then I can engage with you from there. If you don't understand certain things, if you find it difficult to understand certain things, I will explain more on it. If you think I shouldn't dwell or explain too much on certain things, I will avoid from doing so, and so on. Okay, up to you in your own time. I'm not going to force you to do it now. By next class, I hope to see it populated, and then I can, strategize from there. Okay, any questions? It's a very quiet group. Last time I had very too much questions, students. Okay, all right. If there's no questions, then we'll meet next Monday. Okay, next Monday we will have our first physical class. All right. In the meantime, there are exercises in here that you can try. Okay, I haven't gone through slide 31 yet, but it's basically the same thing, except that some examples require you to use table A6. Okay, we will go through more exercises in the next class. More examples. Today is just the first part of the topic, which is just the lecture. The next part of the topic is exercises. Okay, so we will go through exercises on Monday. All right. If there's no more questions, I will end it here. Thank you so much, everyone, for attending today's class. I'll see you next week. Bye-bye. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Okay, you're welcome.
Thank you, Doctor.
Thank you, Doctor.
Okay, bye.